So welcome everyone who's joining us for the recording. Just a couple of remarks before we start on our calculus content today, which is a reminder about the fact that invitations are open for applications to be a leader on the CAME initiative. And my colleague, Dr. Gary Galanders in the School of Physics, has asked me to just remind you about this. Gary is the Vice Dean for Education and Students in the College of Science and Engineering, and you've probably already heard from him. And he just wanted to asked me to remind you about the opportunity to apply to be a leader in the CAME initiative next year. So basically, CAME is an education initiative that's managed and run by the Students' Union. And it's a forum in which people can support each other, essentially, students in learning. And the idea is that groups of first-year students would meet together with CAME leaders from subsequent years, just for conversation, advice, and support in terms of anything related to the academic programs, teaching and learning. It's a program that has sort of grown a lot since its inception a few years ago. And it's something that is, that both people who participate in it, both as student participants and as their peers who are leaders on it, really report very positively on its academic benefits and on a really positive, enjoyable experience. So essentially, it's a forum in which students can help each other with academic work and with general academic support. And I guess we're encouraging everyone to think about volunteering next year to be a CAME leader. Applications are open at the moment, and the information is all there at the Students' Union website on CAME. What it involves is a couple of days of training, working as a team with fellow leaders, and meeting, in your case, it would be first-year students, and you'd be meeting them next year when you're in second year, just for general advice, conversation, and support regarding academic activity. And that generally sort of being a sort of experienced support person for the more inexperienced students who you'd be sort of mentoring as a CAME leader. So that's what's involved. It's an opportunity to develop, I guess, your sort of leadership and communication skills, and as well as also, I suppose, your own education. And it's just something that people find rewarding and supportive and beneficial who've participated in it. So I guess the thing to do if you're interested in applying, I think you've probably also received an email from Claire about it in the recent past in the college office, is just, I guess, have a look at the CAME website and the Students' Union pages, sunuigalway.ie/CAME. Figure out a little bit more about what's involved and consider whether it's something that might interest you. And I guess it remarks that this year is like no other year. And I guess one of the things that Gary highlighted is that there hasn't been as much interest as maybe the college office had hoped for, which I think is completely understandable under the circumstances, given the year that you're having, which is definitely not the introduction to university experience that you would have wished for, or that any of us would have wished you to have. So if you're kind of a bit reluctant to get involved in something like this, in view of that experience, I guess the only remark I would make about that is that, you've shown kind of resilience and persistence and tenacity, unlike anything that has been expected of any students in any preceding year. So you certainly have the skills and experience that would equip you to be very good advisors and role models to future students. I know you haven't had the on-campus experience that we certainly would expect to be part of a third level education. Hopefully that this difficult time will soon be coming to an end. But I think, it's not a reason not to consider contributing to the CAME program if you would have considered it otherwise. I guess it's a remark that I'd make. So I'm passing on this message. The opportunity is there. I guess it's not a normal time, so it's harder to evaluate for yourself whether it's something that you might be interested in or not. But if you are, I'd certainly encourage you to consider filling out the application form and getting involved in that for next year, which hopefully would be a very different one from the current year. Okay, that's a message essentially from the college and from Gary. But I suppose the thing I'd say about the CAME experience, it's new to the science programs, so it's not something that has been experienced before in relation to this particular module, but it's extending year to year, and it's coming to this module now for next year's first year students. And it's one of those rare things where the feedback from everyone who's been involved in it so far across the entire university has been uniformly positive, both from the people who've been participating as leaders, which you're currently invited to consider doing next year, and as student participants. So okay, that's CAME. Okay, I'm going to move on to some calculus and share our lecture notes. Does anybody have a question or comment, by the way, about any of that? If you do, I'm probably, in all honesty, not the best person to answer it, but I will try to put you in touch with somebody who can answer it if you do have a question, and feel free to get in touch with me in that case. Okay, so at this stage, you should hopefully be able to see our calculus notes slides. If you can't, please either shout or put a note in the chat. Okay, so our theme today is the substitution technique for integration. And I know that we started talking about this yesterday, and we're going to continue talking about it today. And essentially, our content today will be a bunch of examples which are to do with practicing this technique. And so, as I said yesterday, the substitution technique, which is the first of 3 specific techniques that we look at, is about reversing the chain rule of differentiation. So instead of going from a function to its derivative, we're going from something to its antiderivative, or we're trying to find something which has our given function as a derivative. And we're dealing in particular with cases where the thing that we're trying to integrate or find an antiderivative for is something that could have been obtained by applying the chain rule of differentiation. So there are a number of obvious problems with that. The first one is you can't really recognize by glancing at something if it has been obtained by applying the chain rule to something else or not. So there's an element of guesswork and of kind of, hopefully kind of smart guessing involved in all of this. It's not something that has hard and fast rules. Okay, and the second thing is, if you sort of think that the substitution technique is something that might work for a particular example, there are still, as we'll see, some sort of options open to you about exactly how you go about applying it that, again, require a little bit of experienced guesswork, I suppose, and a little bit of ingenuity sometimes. So the first example that we looked at yesterday, maybe I'll just return to now. So this is example 19 in our slides. And the problem was to determine the indefinite integral of this expression, 2x times x squared plus 1. Okay, so this is the example that we left off with yesterday. I'm going to just have another look at it now, and maybe in slightly more detail, because it was kind of a slightly rushed job at the end of yesterday's meeting. Okay, so our problem here is to determine the indefinite integral of this expression, 2x times the square root of x squared plus 1. Okay, and just glancing at this, like, it doesn't fit into any of the frameworks that we've seen for our examples that we've looked at so far. It's not a polynomial function of x. It's not something really that we can recognize quickly. So in a case like this, the advice is do whatever you can, essentially. And one of the things that we can do is be on the lookout in a case like this where the integrand here, 2x times x squared plus 1. One thing that we can notice about it is it's a product. It's a product of 2 things, 2x and the square root of x squared plus 1. Okay, fine, we can observe that. Why is that interesting? Well, I suppose when you apply the chain rule to something, what you get is a product. If you're differentiating some expression involving x via the chain rule, let's say you're taking the derivative with respect to x of something which is an expression, some g of x, let's say, or sorry, excuse me, some g which is written in terms of some variable, let's say u. If you want to differentiate that with respect to x, you differentiate it first with respect to u, and then multiply by the derivative du dx. So that's the chain rule. So essentially, you get something which would be a product. And so I suppose that's the observation, that outputs of the chain rule look like products. They have multiple factors, one of which is the sort of derivative of u part, and the other which is the du dx part. So that's fine. So I suppose if something looks like a product, it means there's some chance it might have come from the chain rule somehow. It might be reversible by some means of reversing the chain rule. That's an observation. And the other thing to be on the lookout for in cases like this, and the reason I'm saying all this so vaguely is because it doesn't always work. But sometimes it does, is if you have a product like that and you can sort of notice that there's some part of it. So here we have the square root of x squared plus 1. And inside there is an x squared plus 1. And also elsewhere in our expression, we have 2x. And we might notice, this is the first line here, that the expression that we're trying to integrate involves x squared plus 1, and it also involves 2x. Okay, that's ignoring a lot of details that are there, but it's true. We can also observe that 2x is the derivative of x squared plus 1. Okay, and the advice there when you're dealing with the substitution technique is if you notice something like that, to introduce the notation, and for some reason, I don't know the history, the symbol u is always used here in every single example you ever see about substitution integration. They always use the word u for this new variable that you introduce. So introduce a new name, let's say u, and write u for the thing which appears in your expression and whose derivative also appears there. So in this case, we're introducing the name u and we're writing u to be x squared plus 1. Okay, that's not really doing anything. It's just saying we're giving this thing the name u. So if anything, we're introducing more apparatus for no apparent reason. But the idea is, the strategy is, we're going to try to rewrite the problem in terms of u in the hope that the integration will become easier, that we'll be able to translate it into something that we can deal with. Okay, so that's a hope at the moment. It's not guaranteed that we can do it, but let's try it. And what that means is we're going to try to, so we've got this integration problem, 2x square root of x squared plus 1. We're going to try to rewrite it as an integration problem in u, and hopefully a simpler one. Okay, and part of the point there is that the dx part also has to be somehow translated into u. And that's where the fact that the derivative of x squared plus 1 appears in our expression can sort of become useful. Okay, so we can observe the derivative of u du dx with respect to x is 2x. And so here we're going to do this kind of sleight of hand that is not really warranted by any reasonable mathematical explanation at the moment. We're going to, and I've tried to come back to explain why this is sort of reasonable. We're going to pretend this du dx is a fraction, which of course it isn't. I mean, du dx is notation for a derivative. There's no sense in which it's an ordinary fraction. But we're going to rewrite this as though it were a fraction, rewrite it as du equals 2x dx. Okay, so if you're kind of a bit incredulous about this and doubtful about whether it's a reasonable thing to do, just sort of suspend your skepticism for a minute if you can, and we'll see sort of what's going on here and why it works. Okay, the point of that is that the 2x dx here appears in our integration problem. We've got a 2x and we've got a dx. And we're going to try to rewrite that 2x dx as du. That still leaves the square root of x squared plus 1 part of our problem, but that part is also writable in terms of u. So not only are we going to rewrite square root of x squared plus 1 in terms of u, we're going to write the rest of the expression as well, including the dx part in terms of u and du. Okay, so that's the idea. So du, the 2x dx we're going to rewrite as du, and the rest of the expression we're also going to try to rewrite in terms of u. We'll be left then with a new integration problem, which involves the variable u and du, and we're going to hope that we can deal with that one. So let's see, can we do it? Our problem to begin with was integral of 2x square root of x squared plus 1. The square root of x squared plus 1 is the square root of u, or if you prefer, it's sometimes convenient to write that as u to the power 1/2, because we know how to deal with integrals that are powers of things. And the 2x dx part is du. Okay, so here we've got integral of square root of x squared plus 1, that's u to the 1/2 du. And now suddenly this is something that we can deal with. We've got u to the power 1/2, we're integrating over u. We can find something whose derivative with respect to u is u to the 1/2, because that fits into the framework of things that we know how to do. All we have to do there, all we have to do at this point, is increase the index here, the 1/2 by 1 to 3/2, and divide by the new increased index, which is 3/2. So we get 2/3 u to the 3/2, plus, of course, our constant of integration, because it's an indefinite integral. Okay, so what we're saying is that we've translated the problem in x into this problem in u. That's a problem that we can solve. We can integrate u to the power 1/2 over u by just applying our rules for powers of variables, increase the index by 1 from 1/2 to 3/2, divide by the increased index 3/2, that means multiply by 2/3, and there's our antiderivative. And then finally, because the question was posed to us in terms of x, not in terms of u, we should return the answer in terms of x, and u is x squared plus 1, so 2/3 u to the 3/2 is just 2/3 x squared plus 1 to the 3/2 plus constant. Okay, so this is an answer. I mean, it's a answer about which you might be quizzical before you think about it a bit more, but it is an answer, and we can check that the answer is right. This is something that I really, when you're learning these techniques of integration, which are, I think, quite obscure when you first see them, to be fair, I think it's a good habit to just always check your answer by differentiating it. So we can check by differentiating that the thing we've ended up with is indeed an antiderivative of the thing that we started with. And this also, I think, not only does it confirm that the answer is right, but also I think it sort of gives a little bit of plausibility to the process. What happens to the 2x? Excellent question there in the chat. So what happened to the 2x was it was absorbed into the du via the statement du equals 2x dx. So this pink line is supposed to indicate that. The 2x dx became this du. Because du dx was 2x, so when we did this sort of sleight of hand with the fraction there, rewriting du as 2x dx, the 2x dx part all got absorbed into this du. So I don't think that's a complete answer to your question there in the chat, but that's what happened to it. And I'm going to try to, in the next bit, kind of explain why that is sort of reasonable and not cheating, because it really looks like a dodgy thing to do. But somehow what's going on there is sort of built into the machinery of the chain rule. So I hope that answers it for now, and we'll look at it in a bit more detail in a second. But yeah, it's a very good question, and something that we should all be attending to. What happened to the 2x is really at the heart of this. So if we check by differentiation our answer here, so we've got 2/3 x squared plus 1 to the 3/2. So if you were to differentiate that, essentially, first of all, it's a power. So we should differentiate it as though it were a power. 2/3 outside survives. We get 2/3 times 3/2 x squared plus 1 to the 1/2, which is the 3/2 minus 1, all multiplied by the derivative of x squared plus 1, which is 2x. So the 2/3 and the 3/2 cancel each other, and we're left with the square root of x squared plus 1 times 2x, which is indeed what we would have been hoping for. So at least that might persuade us that the answer is right, even if the method might not be entirely convincing yet. Okay, does anybody have a question about that right now? I'm going to try to explain a bit better what happened to the 2x, which is really the heart of the matter. But before that, if anyone has a question, please feel free to either turn on your microphone or to put it in the chat. But, yeah, that is exactly a good question to ask. Okay, so I'm going to insert a page here and try to explain a little bit more than this very dodgy step 2, what happened to the 2x, or at least why that step is justified. Okay, so let me insert a page of a notebook here. So our problem was to integrate 2x square root of x squared plus 1 dx. Okay, and the first observation was, or the step that we introduced. And if you're puzzled by how we were supposed to know to do this, all I could really say to that at the moment is that's a good reason to be puzzled. There isn't a sort of rule that we can cite that says, how do we know to do this, to write u equals x squared plus 1. So I guess the reason why we might suspect that it might work is because x squared plus 1 appears in our problem, and its derivative 2x also does. And when we're practicing these problems, that's kind of a thing to sort of train ourselves to be on the lookout for. Whenever that happens, it sort of suggests that a substitution of this nature might work. The term substitution, of course, comes from this idea of substituting x for u. Okay, so if we look at, if we do that, and then what we have in our expression is actually the square root of u. So the derivative of the square root of u there well, actually, no, let me say it like this. Yeah, let me say it like this. Sorry. So the problem there is to integrate square root of x squared plus 1, which is the square root of u, times 2x over x, and the 2x happens to be du dx. And the dx is still over there on the other side. That's kind of part of the machinery of the integration notation. But the thing that we're trying to integrate, the 2x times the square root of x squared plus 1, that's the square root of u times du dx. Okay, and of course, I mean, the fact that this example wasn't chosen randomly, it was chosen for this reason, that the 2x which appears here happens to be the derivative of a term that appears in the other factor. And so staring at this thing, we might recognize that this is essentially the result of differentiating some expression involving u with respect to x using the chain rule. Okay, so if we had some expression involving u whose derivative with respect to u was the square root of u, then its derivative with respect to x would be the square root of u du dx. So what we would need to do would be would basically just be to integrate the square root of u with respect to u. Okay. So essentially, an expression whose derivative with respect to u is the square root of u would have derivative du dx times square root of u with respect to x. We're trying to integrate over x, but integrating this thing over x, finding an expression whose derivative with respect to x is this thing, is exactly the same problem as finding an expression in u whose derivative with respect to u is the square root of u. And so that sort of translates into the statement that we can just essentially sort of cancel the dx's here, which is, I'll do it in this sort of pale color because it is sort of a little bit dodgy. It's not really a cancellation that you'd have like for fractions. But what we're saying is, if we had, so we're trying to find something whose expression, whose derivative with respect to x is this thing. The derivative of such a thing with respect to u would just be the square root of u, which means solving the problem that's written here is exactly the same as solving the problem of integrating square root of u with respect to u. Okay, and so really that's what we're doing. That's where the sort of reversal of the chain rule is. The chain rule of differentiation is a much easier thing to write down than this description of how the substitution technique for integration works. The chain rule for differentiation just says you've got a function written in terms of some function u, which is in turn a function of x. Then you can say how its derivative with respect to x depends on its derivative with respect to u, and the derivative of u with respect to x. So you can sort of write it down in one line. Here the sort of reversal of it is kind of buried in this cancellation of the dx's. But in terms of that example that we just looked at, that's where the 2x went. It got absorbed into the du. Okay, so yeah, I hope that helps a bit. I mean, I think it's worth sort of reflecting on when you're working on examples like this. But you'll never see the substitution technique written down as a theorem because it doesn't have a sort of really neat statement like this. It's the machinery of it is sort of incorporated into that step where you rewrite the dx in terms of the du. And I think honestly the way to learn it is by practicing with examples. Does anybody have a question right now, or should we have a look at another example? I'm well aware this watching people doing examples of integration is not a great spectator sport, and I'm very aware of that, and we'll be doing it for a couple more lectures. But I really encourage you to practice with further examples of your own. But here's another one, and this one happens to be from an exam paper in this course from a few years ago. But I suppose that might be worth noting in terms of thinking about what's ahead of us later in the year. And it's an example involving trigonometric expressions. And so here, I suppose, what we'll have to do after the end of this chapter is we'll have a bunch of these techniques in mind, which apply to sort of different types of problems. The substitution technique often applies to problems like this, where you've got a product of things and you're trying to integrate it. And there, the thing to be on the lookout for is a situation where one of the things in your product is the derivative of another one. We'll have other types of expressions as well, which don't necessarily look like candidates for this, but sometimes it's not so obvious. So here, I guess, what are we looking at? We've got cosines and sines in a product. Okay, and again, we have to remind ourselves, what do we know and what do we have to work with? So we know how to integrate cosine, we know how to integrate sine. Those are sort of at the sort of basic level of things that we know how to do, or that we can find in the tables, let's say. And here we've got a product of them. So we don't know how to integrate products. And again, this is just like differentiation. If you want to differentiate a product of two things, you don't just do the two of them separately and multiply. And the same for integration. You can't just kind of deal with the factors separately. But we do know something about cosine and sine. And we know that cosine and sine, for example, are more or less derivatives of each other. Maybe you pick up a negative sign going from one to the other, but apart from that, they're basically derivatives of each other. So here, our thinking should be, I'm looking at this product. I can't do it directly. So I should be on the lookout for something in there, which is the derivative of something else in there. So if, for example, you write u equal to cosine of x, okay, and the goal again is to sort of translate this into some integration problem involving a different variable u, which is an easier integration problem because essentially, like with the last one, some of the complexity of this one has been absorbed into the dx part, which is going to be replaced with du. Okay, so if we write u equal cosine x, for example, and I suppose the motivation for this, if you're really wondering, like, where is this coming from, would be, we know that the derivative of cosine x is minus sine x. And we have a sine x in our expression. So if we write u equal to cosine x, then obviously the cosine cubed x is just a power of u. That's relatively easy to rewrite in terms of u. The sine x part is a problem. But if we write u equal to cosine x, then du dx is minus sine x. Okay, which means, again, sort of fudging the meaning of this notation slightly, that can be rewritten as du equal to minus sine x dx, which means the sine x dx here, which appears in our expression, we can rewrite as not du exactly, but as minus du, and the minus sign is not going to cause us any problems. That's just a constant multiple. Okay, so basically we're in the process of sort of translating this integration problem in x into an integration problem in u. We take u to be cosine x, write the derivative of u with respect to x, rewrite that in terms of how du relates to dx, and then honestly, like, what we're doing is sort of hoping that we can incorporate that into our expression and that it will simplify the translation from x into u. If it doesn't, it probably means that your choice of substitution wasn't a good one and you should try something else. But in this example, when we do the change of variables from x to u, the sine x dx becomes minus du. Okay, so the sine x dx part here, I tried to do some kind of color version, translates into minus du. And the cosine cubed x, so u was cosine x, so cosine x cubed is just u cubed. Okay, so in terms of translating the integrand itself, this is looking better than it was. This is just integrating u cubed over u. We know how to do that. It's just a power of u integrated over u. We just increase the index by 1 and divide by the new index. That's manageable. So this is an example of something where the substitution attempt has been sort of successful, and we're able to do it. So one other thing to be aware of, because this is a definite integration problem, is when you're doing this, keep track. So okay, we've now translated this problem into something we can do, which is very good. We should bear in mind that the limits of integration that were given to us, the 0 and the pi here, those are values of x, they're not values of u. Okay, so just we need to bear that in mind. And for the moment, my suggestion is to bear it in mind by just noting it here, by sort of explicitly noting that they're values of x. Because there is an issue here, that our problem is written in terms of u, and our limits of integration are not values of u, they're values of x. So we need to deal with that. Okay. And there are two ways essentially to deal with it. One is to do the integration over u, take the antiderivative, then rewrite it in terms of x, and plug in the values x equals 0 and x equals pi. An alternative is to rewrite the values of x, which are our limits of integration, in terms of u, which we can also do. So here in the notes, this is how it's done. The lower limit of integration x equals 0. When x equals 0, u is cosine x, so it's cosine of 0, which is 1. And when x equals pi, u is cosine of pi, which is minus 1. So we can either rewrite the limits of integration as values of u, or we can rewrite the antiderivative in terms of x and then plug in the original values of x. In some cases, one of these is easier than the other. In many cases, they're sort of about the same in terms of complexity, and I think this is such a case. But in any case, our integral now, having rewritten it in terms of u, is just the integral of u cubed over u. The limits of integration, if we rewrite them as values of u, are cosine of 0 below, which is 1, and cosine of pi above, which is minus 1. And again, I think it's kind of probably a good habit to kind of note explicitly whether you're talking about values of u or values of x, so you don't get confused if you're looking at it later, or so that you don't potentially confuse somebody who's reading it. Okay, so this is sort of this is now a relatively straightforward antiderivative, no longer a trigonometric thing, just a power of u. Integrate the u cubed, you get u to the 4 over 4. that has to be evaluated at u equals 1 above and u equals minus 1 below. And when we plug in the values, when u equals 1, it's 1 over 4. When u equals minus 1, it's minus 1 to the 4 over 4. And so, in fact, we just get 1/4 minus 1/4, which is 0. But it's not obvious in advance, I think, that this integral is 0. So obviously it means that in terms of the areas involved, there's a negative part and a positive part that cancel each other. Okay, so it's another example that when you've sort of had time to think about this a bit more, you'll recognize as being a kind of a candidate for substitution, because the expression involves a product of factors which are essentially derivatives of each other. Where did the negative sign for du go? Let's see, where did it go? Excellent question. Thank you for raising that. You are right. I think it has actually vanished. Sorry, it should be here. Thanks very much for that comment. Yes, there should have been a negative sign there. Our integral, our sin x dx is minus du, so there is a negative sign outside the whole thing. Sorry for that. Yep. It doesn't actually matter. The answer is still 0, but yeah, there should have been a negative sign there. Sorry for that. So it's here. And it becomes a plus. Yeah, you're right. That negative sign should still have been there. The limits didn't get swapped around. What happened was that that's another good comment. The limits didn't really get swapped around. The lower limit was x equals 0, and that corresponds to u equals 1. The upper limit was x equals pi, which corresponds to u equals minus 1. So the limits didn't get swapped around. Swapping them around would be another way of accounting for the negative sign, but we didn't actually do that. What happened was it just happened that the order of 0 and pi got sort of reversed when we exchanged the values of x for values of u, because the lower limit here actually corresponds to the higher value of u, the upper limit to the lower value of u, but that doesn't matter. Oh, hang on. They got swapped around here. I see what you're saying. Yeah, that's what you're referring to in the chat there. Yeah, okay. So what I'm going to do is rewrite the notes for this example in the published version. Yeah, that did actually, but the negative sign certainly should have been here. Okay, apologies for this mess. I'm going to rewrite this and post a corrected version which accounts for the negative sign on the in the notes. But in any case, the answer is 0, fortunately, because it's still going to be 1/4 minus 1/4. Apologies for that, and thanks very much for pointing it out. Okay, here is hopefully a more reliable example. Okay, so here's another one, and this time the expression is, again, a different looking thing. So here it's a rational function involving some variable called r. We've got 5r in the numerator, we've got 4 plus r squared in the denominator. And so as it stands, like, this is not a horribly complicated thing generally, but it's something that we have essentially really sort of no idea how to integrate. We don't have a quotient rule for integrations. There's no version of that. We've got, again, an expression where we've got a quadratic part, this r squared part, that's all squared. So there's a degree 4 part in the denominator, and there's a degree 1 part in the numerator. And again, you know, kind of, it's not that it's obvious that a substitution technique will work here, but a substitution technique is basically something that we can try, and we can hope that it might work. And again, what we can observe is that the numerator has 4 plus r squared in it. The derivative of r squared, or of 4 plus r squared, is 2r, which sort of resembles what's in the denominator. So, and here, I mean, that's kind of all we can really say. So the derivative of 4 plus r squared resembles the numerator. And what I mean by that is that it's a scalar multiple. It's a constant multiple of 5r. So the derivative of 4 plus r squared is 2r. That looks sort of like 5r. So that gives us a reason to expect that substituting u equals 4 plus r squared and translating everything into u might succeed. Okay, so again, the suggestion for the substitution is u equals 4 plus r squared. The reason for that suggestion is that the derivative of that looks sort of like what we have in the numerator and might enable us to sort of to manage that 5r dr part and absorb it into du. Okay, and if we can do that, well, then at least we can sort of rewrite everything in terms of u, and we might have some hope of being able to solve the problem that we have in terms of u. Okay, so if we write u equals 4 plus r squared, then du dr, derivative of u with respect to r is 2r. Du then is 2r dr, and 5r dr, which actually does appear in our problem, would be 5 over 2 times du. Okay, and certainly we can replace the 5r dr with 5 over 2 times du, and the advantage of that is it doesn't have a u in it anymore, so it's certainly simpler than what we started with. And then we have to worry about whether we can translate everything else in terms of u, and then hopefully, if we can, whether we can integrate what we end up with. So the okay, so rewriting the problem, then we've got, this is what we started with, 5r over 4 plus r squared all squared. The 5r dr becomes 5 over 2 du, and what's left after that is 1 over 4 plus r squared all squared, and that is 1 over u squared. Okay, so this bit is the 1 over 4 plus r squared squared part. So what we end up with, rewriting everything in terms of u, is 5 over 2 times integral of 1 over u squared, which we can write as u to the power minus 2, because it's certainly easier to deal with these powers when they're written in that form with a number as the index. Okay, so integrate u to the minus 2. This fits into our program for generally integrating powers. Increase the power by 1 and divide by the new power, which is minus 1. So taking the indefinite integral of 5r over 4 plus r squared, we get 5 over 2 times minus 1 over u, which is minus 5 over 2 times 1 over u. So that's the indefinite integral. Okay, and of course, we weren't asked for the indefinite integral. We were asked for the definite integral with limits 0 and 1, which were values of the original r. So at this point, this is something that I did not explain well in the last example. We have two choices for what to do. We can either rewrite our antiderivative in terms of r and then plug in the values of r, or we can translate our values of r into values of u and do the final kind of calculation in terms of either one of these two variables, r or u. And in some examples, there's a good reason to do one or the other. One of them is just much simpler than the other. In this example, it doesn't matter a whole lot, but we can do either of them. So anyway, in any case, the substitution process is all here. And I guess I should also say, if you're looking at examples like this, it can be a bit frustrating because it quite often happens that you have what you think is a good choice for a change of variables, and you sort of rewrite everything, and you're still left with something lying around that still has an x in it or an r, and that you can't translate into the new variable u. And if that happens, and if you just can't do it, if you can't rewrite some element of your problem in terms of the new variable, it probably just means it wasn't a good choice as a substitution strategy. And it's also not true that every problem can be solved with a substitution of this nature. So it might just mean you need a different strategy if that occurs. And of course, in the lecture notes, we pick examples that are amenable to solutions. So, try not to let it be a frustration if not every example that you look at admits a solution of this type. Some of them sometimes they just don't. Okay, so two choices here for what to do. So our problem now at this stage is we've got our expression that we need to evaluate is minus 5 over 2 times 1 over u. And our limits of integration are 0 and 1, which are values of r. And u is 4 plus r squared. Okay, so one option for proceeding at this point is to rewrite u in terms of r. Our integral is minus 5 over 2 times 1 over u. That's 1 over 4 plus r squared. Evaluate that at r equals 1, at r equals 0. When r is 1, this is minus 5 over 2 times 1 over 5. When r is 0, it's minus 5 over 2 times a quarter. 4 plus 0 squared is a quarter, or is 4. And when we calculate that, we get 1/8. Okay, so that's sort of the, I suppose, the direct way to deal with it. Leave the limits of integration where they were, rewrite everything in terms of the original variable, and plug in the values of the original variable, which was r. And the alternative is, instead of doing that, instead of writing your integral in terms of the original variable, write the original limits in terms of the new variable and plug those in, and you should get the same answer. So the alternative is to write the antiderivative, which was minus 5/2 times 1/u, and replace the limits of integration with the corresponding values of u. So the limits of integration were r equals 0 for the lower limit. That corresponds to u equals 4 plus 0 squared, which is 4. R equals 1 for the upper limit, which corresponds to u equals 4 plus 1 squared, which is 5. And there, the problem's essentially the same. The only difference is you're leaving everything written in terms of u and plugging in the two values of u instead of the two values of r, and hopefully we get the same answer. The negative sign for 5/2. Okay, let's see, where did that come from? That came from, okay, yeah. So the negative sign is not really on the 5/2, it's on the 1/u. So when we were doing the integration, we had to integrate u to the power minus 2. And when you do that, we increase the power by 1, which gives us u to the minus 1, and we divide by the new power, which is minus 1. So that negative sign that ended up there is the negative sign that turned up when we integrated u to the power minus 2. I just pulled it out here. Does that answer it? So in this case, it definitely is supposed to be there. Yeah, okay, great. Thanks for that question. It's a good one. Yeah, and with these things, it's so easy to sort of lose track of signs and bits and pieces like that are lying around the place. So just try to be careful in your own sort of system for keeping track of everything when you're writing, of keeping track of signs. Also, the fact that when you're plugging in the limits of integration, you're plugging in the r equals 1 from that, you're subtracting the value at r equals 0, and there's a whole load of negative signs around, and it really takes a bit of care to keep track of all of them. But in any case, I mean, the principles are more important. Accidents with signs or whatever don't matter so much at the end of the day, but they're very easy to make in these kinds of examples. And it can be quite frustrating if you're working on some problems and checking the answers in the back of the book, that your answer doesn't agree with the back of the book, and you realize it's because of some stray sign somewhere. It's quite difficult to track down when you're going through it again. So yeah, so just be on the lookout for that. Okay, so yeah, so the point there really of that example is just that we have a choice to make if you're doing a definite integration problem with substitution about whether you want to rewrite the limits of integration in terms of the new variable, or whether you want to rewrite the integral in terms of the original variable and plug in the original values. And I suppose the thing to be aware of is sometimes one of those is a bit of a chore and the other one's much easier. In this particular example, they're kind of about the same, but occasionally one of them is more manageable than the other. Okay, those are a few examples with substitution. They're sort of, I suppose, reasonably representative. I know it's not exactly the world's best spectator sport to watch somebody else go through these examples, especially when they end up chasing missing signs around the place. So I apologize for that one. Would it be helpful to post a few more of them in a sort of supplementary little video tutorial? Just put a yes in the chat if you think it would. Or definitely not if you've really seen enough of this. Okay. So there seems to be a few votes for yes. There's no obligation, of course, to go through it all, but maybe it'll be helpful. And there are more of them also in the lecture notes. But I guess the thing I'd say to everybody is, practice with your own examples as well. Don't just look at these ones, because you really get a sense of it by practicing with your own. So I'll post a few minutes of extra examples on this technique and try to get them right. And it's something worth practicing. So if you have access to Stuart's calculus book, the link to it in the library copy is on the front page of our website. You'll find endless examples there. So working through sort of 5 or 6 of them when you have a couple of hours to spend on it is definitely the best way to practice this technique. And there are plenty of examples also in the text there, of course. Okay, that's essentially what we have for this week. I'm going to stop the recording, and thank you everyone who's joined us for the recording. See you next week.